Alpha Centauri lies just over 4 light-years away. In cosmic terms, that distance is almost nothing. Light itself crosses it in a little more than 4 years. A signal sent today would arrive before the end of this decade. Compared to every other star in the night sky, Alpha Centauri feels reachable, familiar, almost within grasp. For 60 years, scientists, engineers and dreamers quietly treated this system as humanity's first destination beyond the Sun. When people spoke about interstellar probes, Alpha Centauri was the unspoken assumption. When science fiction imagined humanity's future among the stars, this system was often the first stop. It was close enough to matter, close enough to plan for, close enough to hope. That hope grew stronger as astronomy advanced. We learned that Alpha Centauri is not a single star but a family. A small red dwarf, Proxima Centauri, and 2 larger stars remarkably similar to our own Sun. A system that seemed to offer variety, stability, possibility. If life could exist anywhere beyond Earth, surely it would exist here. Then came the discovery that transformed quiet optimism into global excitement. A planet roughly Earth-sized orbiting within the region where liquid water might exist. Proxima B was announced as a potentially habitable world just next door in cosmic terms. Headlines followed. Papers followed. Speculation followed. The universe appeared to have placed a promising planet exactly where we needed it most. For the first time in history, humanity could realistically imagine studying the atmosphere of a nearby exoplanet in detail. We could imagine probes traveling between stars within a human lifetime. We could imagine that the silence between the stars might soon be broken, not by theory, but by data. Alpha Centauri became more than a star system. It became a symbol, a test case, a proving ground. If life existed there, it would mean the universe was generous. If life could not exist there, it would mean something far more unsettling. Because if even the closest stars are hostile to life, then distance is not the true barrier. Physics is. When the James Webb Space Telescope turned its gold-coated mirrors toward Alpha Centauri, it did not look for wonder, it looked for evidence. For signatures written in light itself. For the quiet chemical fingerprints that no imagination can fake. What it found would not extend humanity's hopes outward, it would collapse them inward. And in doing so, it would force us to reconsider not just where life might exist, but how rare our own world may truly be. At first glance, Alpha Centauri does not look like an alien place. It looks reassuringly ordinary. The system is composed of 3 stars bound together by gravity. 2 of them, Alpha Centauri A and Alpha Centauri B, are strikingly similar to our own Sun. One glows with a warm yellow light, slightly brighter and slightly larger than the star that sustains life on Earth. The other burns a softer orange, cooler and dimmer, but still stable and long-lived. Together they form a binary pair that seems almost comforting in its familiarity. The third member, Proxima Centauri, is different. Smaller, dimmer, a red dwarf. But red dwarfs are not rare curiosities. They are the most common stars in the galaxy. Nearly 3 out of every 4 stars in the Milky Way belong to this class. If life exists elsewhere, statistically speaking, it is most likely orbiting a red dwarf. This combination made Alpha Centauri feel like a perfect miniature of the galaxy itself. A sun-like star, a cooler companion, a red dwarf representing the dominant stellar population of the universe. Nothing about this system appeared extreme. Nothing suggested violence or instability at first glance. These stars were old billions of years in age. They had existed long enough for planets to form cool and evolve. Long enough for chemistry to organize itself into something more complex if conditions allowed. From Earth, Alpha Centauri A and B appear as a single bright point of light in the southern sky. Only telescopes reveal their slow gravitational dance around one another. They complete a full orbit every few decades, close enough to interact but far enough apart to seem manageable. For years, astronomers debated whether planets could form and survive in such an environment. Some simulations suggested problems, others suggested narrow windows of stability. And then there was Proxima Centauri, a small star but a quiet one. At least that was the assumption. before high-precision space observatories Proxima appeared unremarkable. Occasional stellar flares had been detected, but nothing that seemed catastrophic. Many researchers believe that planets with thick atmospheres or strong magnetic fields could withstand such activity. After all, Earth itself survives solar storms. Why should a nearby planet not do the same? The system seemed to offer multiple chances. If planets failed around one star, perhaps they survived around another. If one environment proved hostile, another might compensate. Alpha Centauri did not look like a dead end. It looked like a crossroads. A nearby laboratory where theories about habitability could finally be tested against reality. A place where optimism could be refined into understanding. Where speculation could be replaced by measurement. But familiarity can be deceptive in astronomy. Stars that resemble the Sun do not always behave like the Sun, and proximity does not guarantee safety. The closer we looked at Alpha Centauri, the more important the details became. Details that could not be guessed from afar. Details that only precise instruments could reveal. And as those instruments improved, the comforting image of a familiar stellar neighborhood began to fracture. The turning point came quietly, as many scientific revolutions do. Not with an image, but with numbers. In 2016, astronomers analysing subtle wobbles in Proxima Centauri's motion announced the presence of a planet, a small persistent gravitational tug, too regular to be noise, too precise to ignore. Proxima B had revealed itself not through light, but through influence. The measurements were immediately arresting. The planet's mass was close to that of Earth. Not a gas giant, not a frozen dwarf, a rocky world. Even more striking was its orbit. Proxima B circled its star at just the right distance to receive roughly the same amount of energy that Earth receives from the Sun, warm enough, at least in principle, for liquid water to exist on its surface. This was not just another exoplanet. This was the exoplanet. For decades, astronomers had searched hundreds of light-years outward, cataloguing worlds that were too hot, too cold, too massive, or too distant to study in detail. And now, almost immediately, a planet with Earth-like characteristics appeared orbiting the nearest star to our own. The coincidence felt uncanny. If the universe were arranging a demonstration, this is where it would place it. Proxima B ignited imaginations precisely because it seemed so accessible. Its star was close enough for detailed follow-up observations. Close enough for future telescopes to probe its atmosphere. Close enough that concepts like interstellar probes stopped sounding like fantasy and started sounding like engineering problems. Scientists began asking careful questions. Could Proxima B retain an atmosphere? Could it possess oceans beneath alien skies? Could life have emerged there, perhaps microbial, perhaps adapted to dim red starlight? The planet's proximity allowed these questions to feel tangible rather than abstract. Public interest followed scientific curiosity. Proxima B became a symbol of cosmic possibility, a reminder that Earth might not be alone and that proof of that fact might lie just beyond the reach of our current technology. Yet even as optimism spread, a quiet tension lingered beneath the excitement. Proxima B orbited extremely close to its star, so close that a year on that world lasted only 11 Earth days. Such proximity raised unavoidable physical consequences: tidal forces, radiation exposure, stellar behavior that could no longer be averaged away. The habitable zone label began to do heavy emotional work. It suggested safety. It suggested balance. But it concealed assumptions that had not yet been tested. Proxima B did not prove that life existed nearby. It posed a far more dangerous question. What if a planet can sit in the right place and still be completely uninhabitable? To answer that question, astronomers needed more than orbital data. They needed to see how the planet's star behaved not occasionally but constantly. They needed to know what kind of environment Proxima B had endured for billions of years, and that meant waiting for a telescope capable of turning speculation into measurement. That telescope was already on its way. The phrase habitable zone carries a dangerous simplicity. It sounds definitive. As if crossing an invisible boundary in space suddenly transforms a planet from lifeless rock into a potential Eden. In reality, the habitable zone describes only one condition: temperature. It marks the region around a star where a planet could in theory maintain liquid water on its surface. Nothing more, nothing less. It does not guarantee oceans. It does not guarantee air. It does not guarantee protection from the star itself. For years, astronomers treated this zone as a useful first filter. With thousands of exoplanets to catalogue, it provided a way to narrow the search. But over time, the label began to carry implications it was never meant to hold. In public imagination, and sometimes even in scientific shorthand, habitable became conflated with inhabited. Proxima B exposed how fragile that assumption really was. To remain truly habitable, a planet must satisfy a long list of requirements simultaneously. It must hold on to an atmosphere for billions of years. It must shield its surface from harmful radiation. It must maintain chemical stability long enough for complex molecules to form, accumulate, and interact. It must experience relative calm not just occasionally but persistently over geological time. Temperature alone cannot provide any of this. A planet can sit comfortably within the habitable zone and still be stripped bare by stellar winds. It can be warm enough for water yet lose that water molecule by molecule to space. It can orbit at the right distance and still be sterilized repeatedly by radiation powerful enough to destroy organic chemistry before it ever has a chance to organize. Red dwarf stars complicate this picture further. Because they emit far less light than stars like the Sun, their habitable zones lie much closer in. Planets must huddle tightly around them to receive enough warmth. This proximity exposes those worlds to intense gravitational forces, powerful magnetic interactions, and stellar activity that would be irrelevant at larger distances. The habitable zone around a red dwarf is not a gentle band of possibility. It is a narrow ring carved out of danger. Before James Webb, much of this remained theoretical. Models suggested problems, simulations warned of risks. But without detailed observations, hope persisted. Perhaps thick atmospheres could compensate. Perhaps magnetic fields could deflect radiation. Perhaps life could adapt as it so often does on Earth. Proxima B became the test case for these ideas, a real planet close enough to observe orbiting the most common type of star in the galaxy. If habitability could survive under these conditions, it would dramatically expand the number of potential life-bearing worlds in the universe. But if it could not, then the habitable zone would reveal itself not as a promise, but as a misleading simplification, a concept that hides as much as it reveals. To move beyond assumption, astronomers needed to look directly at the environment surrounding Proxima B, not just where it orbited, but what it endured. Not just how much light it received, but what kind of light, how often, and with what consequences. That required an instrument capable of seeing planets not as points, but as physical worlds shaped by their stars. And when that instrument finally arrived, it would show that the true boundary of habitability is not drawn by distance alone. When the James Webb Space Telescope finally began its observations, it did not arrive with drama. There were no sudden revelations, no single image that changed everything overnight. What Webb delivered instead was something far more disruptive. Precision. Unlike previous telescopes, James Webb was built to read the universe chemically. Its gold-coated mirror does not simply collect light, it dissects it. By separating starlight into its component wavelengths, Webb can detect the faint fingerprints left behind when light passes through gas dust or atmosphere. Each molecule absorbs light in its own distinctive pattern. Water vapor leaves one signature, carbon dioxide another, oxygen, methane, ammonia each announces its presence through physics that cannot lie. This capability transformed exoplanets from distant dots into testable worlds. For Proxima B, the expectations were cautious but hopeful. Even a thin atmosphere should have revealed itself through spectral features. A dense carbon dioxide envelope like that of Venus would be unmistakable. Water vapor, even in small quantities, would leave clear absorption lines. Webb did not need to find life, it only needed to find air. The telescope observed Proxima Centauri repeatedly, monitoring its output across infrared wavelengths, while tracking how that light interacted with its surroundings. It measured stellar activity continuously, not just during rare flares, but across normal cycles. It watched the system over time, building a statistical picture rather than relying on snapshots. This was the critical difference. Earlier observations had caught Proxima during isolated outbursts. Webb revealed what happened between them. The baseline, the background state, the environment a planet would experience every day, every orbit for billions of years. As the data accumulated, a pattern began to emerge. Proxima Centauri was not a calm star punctuated by occasional violence. It was an active star punctuated by brief moments of relative calm. Flares were not anomalies. They were routine. Bursts of radiation surged outward repeatedly, sometimes increasing the star's energetic output by orders of magnitude in minutes. For astronomers, this alone was troubling. But the real test came when Webb searched for the atmospheric signatures around Proxima B itself. The analysis was unforgiving. Where models predicted absorption lines, there was silence. Where theory allowed for carbon dioxide or water vapor, the spectra remained flat. The planet did not imprint itself on starlight in any detectable way. In science, absence can be more decisive than presence. An atmosphere thick enough to support surface water should have announced itself loudly. Even a world in the process of losing its air should have left traces behind. Webb found neither. The implication was stark. Proxima B was not hiding its atmosphere. It did not have one. What had once been imagined as a nearby Earth analogue was beginning to resemble something far more familiar and far more barren. A rocky body exposed directly to space, stripped clean by forces that operate silently but relentlessly. James Webb had not looked at Proxima B and found ambiguity. It had looked closer and removed it. And with that clarity came a realization that would ripple far beyond a single planet. The absence of an atmosphere around Proxima B demanded an explanation. Planets do not simply lose air without cause. Something had to remove it. Something persistent. Something powerful. James Webb's data pointed unmistakably to the source. Proxima Centauri is a red dwarf, and red dwarfs live by a different set of rules than stars like our Sun. Instead of having layered interiors where energy moves slowly outward, Proxima is fully convective from core to surface. Hot plasma rises, cool plasma sinks, and the entire star churns continuously like a boiling pot. This motion twists magnetic field lines into stressed, tangled configurations that store enormous amounts of energy. When those magnetic fields snap and reconnect, the energy is released violently. Webb revealed that these events are not rare. Proxima Centauri produces significant flares multiple times each week, with smaller eruptions occurring almost daily. During major outbursts, the star's brightness in high-energy wavelengths surges by factors of hundreds or even thousands. Ultraviolet and X-ray radiation floods the surrounding space in sudden waves. For a planet orbiting at a comfortable distance, such events might be survivable. Proxima B does not orbit at a comfortable distance. The planet circles its star at roughly 7.5 million kilometers. That is about 20 times closer than Earth is to the Sun. At that range, every flare strikes with devastating intensity. Radiation levels during large events exceed what Earth receives during severe solar storms by orders of magnitude. And unlike Earth, Proxima B has no thick atmosphere or magnetic shield to absorb the blow. What Webb revealed was not a star that occasionally lashes out. It revealed a star that never truly rests. Between flares, Proxima remains magnetically active. Its stellar wind streams of charged particles flowing outward from the star is dense and fast. These particles collide directly with any planetary surface or atmosphere in their path. Over time, they erode, strip and scatter molecules into space through a process that cannot be reversed without protection. This constant assault changes the meaning of habitability entirely. Proxima B is not challenged by rare catastrophes. It is subjected to continuous attrition, Every orbit, every day, every year, the star works to dismantle whatever fragile structures might exist on the planet. Any atmosphere that formed early would have been stripped away within tens or hundreds of millions of years. Any water exposed at the surface would have been broken apart by ultraviolet light, its hydrogen drifting irretrievably into space. Any complex organic molecules would have been destroyed faster than they could accumulate. The violence is not temporary. Red dwarfs burn slowly, remaining active for trillions of years. Proxima Centauri shows no sign of calming with age. Despite being roughly as old as the Sun, it continues to behave like a much younger, far more volatile star. For lifetime is everything. For Proxima B time is the enemy. What James Webb uncovered was not merely a hostile environment, but a fundamentally incompatible one. A place where the processes that allow life to begin are undone faster than they can proceed. And this realization carried consequences far beyond a single planet. Once the behavior of Proxima Centauri was understood, the fate of Proxima B's atmosphere followed from first principles. There was no mystery left to solve, only physics unfolding over time. An atmosphere exists in a delicate equilibrium. Gas molecules are constantly moving, constantly colliding, constantly testing the grip of gravity. On Earth, most of them fail to escape. Our planet is massive enough, cool enough, and protected enough to keep its air for billions of years. That protection is not accidental. It is the product of distance magnetic shielding and a star that radiates with relative restraint. Proxima B occupies a very different regime. Ultraviolet radiation from its star penetrates the upper layers of any atmosphere with ease. Each photon carries enough energy to break molecular bonds. Water vapor splits into hydrogen and oxygen. Carbon dioxide fractures into lighter components. Once broken apart, the fragments no longer behave like stable gases. Hydrogen, the lightest element, escapes almost immediately into space. At the same time, Proxima Centauri's stellar wind applies a continuous mechanical force. Streams of charged particles slam into the upper atmosphere, transferring momentum molecule by molecule. This process, known as sputtering, knocks atmospheric gases upward until gravity can no longer hold them. The loss is slow on human timescales, but relentless on geological ones. James Webb's measurements allow these processes to be quantified. For a planet like Proxima B, an Earth-like atmosphere would survive no more than a few tens of millions of years. Even a much thicker atmosphere would fare little better, extending survival by hundreds of millions of years at most. The planet itself has existed for nearly 5 billion years. The imbalance is decisive. Any air Proxima B once possessed would have vanished long before life had time to begin. Prebiotic chemistry requires stability. Complex molecules must accumulate, persist, and interact over immense spans of time. On this world, the chemical foundation is erased faster than it can assemble. The absence of an atmosphere is not a recent development. It is the natural endpoint of billions of years of exposure to a violent star at close range. A bare surface remains directly exposed to radiation particle bombardment and the vacuum of space. Without air, there is no pressure to support liquid water. Without air, there is no shield against ultraviolet radiation. Without air, there is no medium to transport heat or sustain chemistry. The planet is not dormant. It is stripped. At this point, the conversation about habitability changes character. The issue is no longer whether Proxima B could maintain Earth-like conditions. It is whether it could ever maintain any conditions in which life might gain a foothold. And the evidence points in only one direction. Once an atmosphere is gone, a planet does not merely become inhospitable. It becomes exposed in the most literal sense. Space presses directly against rock, and every physical process accelerates toward loss rather than balance. Water is the first casualty. On a planet like Proxima B, any surface water that might have existed early in its history would have faced immediate destruction. Ultraviolet radiation breaks water molecules apart through photodissociation. The hydrogen escapes easily, drifting into interplanetary space where it is never recovered. Oxygen, heavier and more reactive, follows more slowly or binds chemically to surface minerals. Over time, this process drains a planet dry. Without an atmosphere, there is no way to trap evaporated water. There is no pressure to keep it liquid. Even ice offers no refuge. Exposed ice sublimates directly into vapor under stellar radiation molecule by molecule until nothing remains. A planet does not need to be hot to lose its water. It only needs to be unprotected. Some models once suggested that life might survive below the surface. That idea collapses under closer examination. High-energy particles from Proxima Centauri's frequent flares penetrate meters into rock. Radiation does not stop at the surface. It seeps downward, degrading chemistry and damaging molecular structures even in shallow subsurface environments. On Earth, early life likely found refuge beneath oceans where hundreds of meters of water absorbed harmful radiation. Proxima B has no such shield, no ocean, no thick ice cap, no stable underground environment connected to energy sources and chemical gradients that life requires. Every potential sanctuary is compromised. The surface is sterilized repeatedly by radiation. The subsurface is irradiated without relief. The planet's chemistry is constantly reset to a simpler, more barren state. This is not a world waiting quietly for conditions to improve. There is no recovery mechanism. Volcanic outgassing, if it occurs at all, cannot rebuild an atmosphere faster than the star strips it away. Any gases released would either escape immediately or be broken apart before they could accumulate. Time offers no second chance. In planetary science, habitability is not judged by brief moments of possibility. It is judged by endurance. A world must remain chemically and physically stable long enough for complexity to arise. Proxima B fails that test decisively. What remains is not a marginally hostile environment. It is an environment where every pathway toward life is cut off simultaneously. At this point, the question is no longer whether Proxima B could resemble Earth. It is whether life of any kind could ever have persisted there at all. And the answer continues to narrow. Even if Proxima B had somehow retained a thin atmosphere longer than expected, another constraint would still dominate its fate. Distance alone guarantees it. The planet orbits its star once every 11 Earth days. At such close range, gravitational forces act relentlessly on its rotation. Over time, those forces slow the planet's spin until rotation and orbit synchronize. One hemisphere becomes permanently exposed to the star. The other is locked in perpetual darkness. This state is known as tidal locking, and for Proxima B it is not a possibility. It is a certainty. On a tidally locked world, sunlight never rises or sets. The day side receives continuous radiation. The night side receives none at all. Without an atmosphere to transport heat, temperatures diverge dramatically. The illuminated hemisphere heats until rock itself can glow. The dark hemisphere cools toward the temperature of deep space. James Webb's measurements of infrared emission are consistent with this outcome. The thermal contrast inferred for Proxima B exceeds anything found on Earth or even Mars. The difference between hemispheres likely spans more than 1,000 degrees. No known biological chemistry can operate across such extremes. In theory, a sufficiently dense atmosphere could soften these conditions. Winds could carry heat from day to night. Oceans could absorb energy and redistribute it slowly. But those solutions depend on the very thing Proxima B lacks: air. Without an atmosphere, heat does not flow. It accumulates. The dayside bakes continuously, driving any remaining volatiles away. The night side becomes a cold trap where gases would freeze out permanently if any existed at all. This process, known as atmospheric collapse, ensures that even a marginal atmosphere cannot survive long-term on a tidally locked world under intense stellar radiation. The geometry of the planet itself becomes hostile. There is no stable middle ground. The narrow twilight region between light and dark is not a refuge but a zone of violent thermal gradients. Rock expands and contracts. Surface materials fracture. Chemistry is disrupted before it can stabilize. Tidal locking also weakens another critical defense. Planetary magnetic fields depend on rotation. Slower rotation reduces the ability of a molten core to generate a coherent magnetic dynamo. For Proxima B, one rotation every 11 days is far too slow to sustain a protective magnetic field comparable to Earth's. Without that field, stellar wind particles strike the planet, directly accelerating atmospheric loss and surface damage. The same proximity that provides warmth ensures destruction. Taken together, these effects leave no room for adaptation. The planet is not merely hostile. Its fundamental configuration prevents moderation. There is no cycle to soften extremes, no variability to create niches, no long-term stability on which life depends. Proxima B does not fail because it is unlucky. It fails because its orbit dictates its physics. And this realization transforms the story from a single planet's misfortune into a broader warning about where habitability can and cannot exist. Proxima B's failure is not an isolated tragedy. It is a consequence of the kind of star it orbits. Red dwarfs appear at first to be ideal hosts for life. They are small, efficient, and extraordinarily long-lived, while stars like the Sun will exhaust their fuel in a few billion years. Red dwarfs burn so slowly that they can shine for trillions. On paper, that longevity seems like a gift to biology. More time should mean more opportunity. But red dwarfs pay for their efficiency with instability. Unlike the Sun, which transports energy outward through layered regions that dampen turbulence, red dwarfs are fully convective. Hot plasma rises directly from the core to the surface while cooler material sinks back down. This constant churning twists magnetic field lines into dense, stressed knots that store vast amounts of energy. Those knots do not remain stable. When magnetic field lines reconnect, they release that energy explosively, producing flares that dwarf anything our Sun routinely generates. A strong solar flare might briefly increase the Sun's brightness by a fraction of a percent. A strong red dwarf flare can increase high-energy output by factors of hundreds or more, and these events do not fade with age. James Webb's observations confirm that Proxima Centauri, despite being billions of years old, remains intensely active. Its magnetic dynamo shows no sign of settling down. The violence is not a youthful phase, it is a permanent condition. This matters because planets in red dwarf habitable zones must orbit close to receive enough warmth. That proximity places them deep inside the star's magnetic environment, where flares, ultraviolet radiation, and dense stellar winds are unavoidable. The same closeness that provides heat guarantees exposure. There is no safe compromise distance. Move a planet farther out and it freezes. Move it closer in and it is stripped. The habitable zone becomes a narrow corridor where thermal conditions are acceptable, but radiation conditions are lethal. For decades, some scientists hoped that thick atmospheres or powerful magnetic fields could compensate. James Webb's data suggests otherwise. The energy delivered by red dwarf activity overwhelms any plausible planetary defense. Even Earth's magnetic field, if placed at Proxima B's orbit, would collapse under the pressure of such intense stellar wind. This is why Proxima B matters so deeply. Red dwarfs are not rare edge cases. They dominate the galaxy. If their environments are fundamentally hostile to long-term habitability, then the universe contains far fewer viable homes for life than optimistic models once assumed. The betrayal lies in the illusion of suitability. Red dwarfs offer warmth without mercy, time without calm, energy without restraint, and in doing so, they reveal that longevity alone is not what life requires. Stability is. What happened around Proxima Centauri forces astronomers to confront a sobering possibility. The most common stars in the galaxy may also be the least capable of supporting life as we understand it. Once Proxima Centauri was understood, it stopped being a special case. It became a reference point. James Webb did not observe this star in isolation. Over the same observing cycles, the telescope examined dozens of other red dwarfs at varying distances and ages, different masses, different metallicities, different evolutionary histories. What emerged from that broader data set was not diversity but consistency. The behaviour seen at Proxima Centauri was not extreme. It was typical. Flare frequencies clustered within the same narrow range. Ultraviolet output followed similar patterns. Stellar wind densities showed comparable strengths when scaled for distance. The nearest red dwarf turned out to be an ordinary representative of its class, not an unusually violent outlier. This realization changed the scale of the problem. If Proxima Centauri were unique habitability around red dwarfs could still survive as a statistical hope. A few unlucky systems would fail, others might remain calm enough to host life, but James Webb's measurements closed that loophole. The physics driving red dwarf activity appears universal, rooted in fully convective interiors that do not quiet with age. Red dwarfs remain active for as long as they shine, and they shine for trillions of years. For planets orbiting these stars, the implication is brutal. Atmospheric erosion does not slow down. Radiation exposure does not taper off. There is no late peaceful phase when conditions might finally stabilize. The window for habitability does not open later. It never opens at all. This forces a re-evaluation of one of astronomy's most influential assumptions. Because red dwarfs are so numerous, many models of galactic habitability relied on them. Even if only a small fraction hosted life, their sheer abundance would still dominate the cosmic census. Red dwarfs were expected to be the backbone of biological opportunity in the Milky Way. James Webb suggests the opposite. If red dwarfs systematically strip atmospheres, destroy surface water, and sterilize planetary chemistry, then their planets cannot contribute meaningfully to the population of habitable worlds. A category that once accounted for the majority of stars may now account for almost none of the viable habitats. The universe does not lose a few candidates, it loses most of them. This shift ripples outward into every estimate of life beyond Earth. Calculations that once yielded billions of potentially habitable planets now collapse under stricter physical constraints. The number shrinks not because of pessimism, but because measurement has replaced assumption. Proxima Centauri delivered the first clear signal. James Webb confirmed that it was not alone, and with that confirmation attention turned elsewhere. If the most common stars cannot host life, perhaps the answer lies with stars more like our own. Stars that burn calmly. Stars that offer distance without deprivation. Hope once again began to migrate. This time toward the two bright suns at the heart of the Alpha Centauri system. With Proxima Centauri effectively ruled out, attention shifted inward toward the brighter heart of the system. Alpha Centauri A and B no longer represented supporting characters in the story. They became its last remaining hope. These two stars resemble the Sun in ways that matter deeply for habitability. Their internal structures are layered rather than fully convective. Energy moves outward more gradually. Magnetic fields are less chaotic. Their radiation output varies but within limits familiar to life on Earth. Compared to a red dwarf, they are restrained. Their habitable zones lie farther out at distances where tidal locking is no longer inevitable, and where stellar winds weaken with space. A planet orbiting either star at the right range could, in principle, experience stable days and nights, moderate radiation, and a climate capable of persistence rather than extremes. On paper, these stars look like redemption. Alpha Centauri. A shines slightly brighter and slightly larger than the Sun, a close sibling that formed from similar interstellar material. Alpha Centauri B is cooler and dimmer but still stable over billions of years. Together they span the range of stellar conditions under which life is already known to exist. If habitability had failed around Proxima because of stellar violence, perhaps it could survive here through moderation. This hope was not naive. It was grounded in decades of planetary science. Around solitary stars like the Sun, planets form naturally from disks of gas and dust. Rocky worlds emerge close in, gas giants form farther out. Volatiles are delivered gradually. Atmospheres stabilize. Oceans persist. For years, astronomers debated whether this same process could operate in a binary system like Alpha Centauri A and B. Some models suggested narrow zones of stability, Others predicted long-term disruption. Without direct observations, both views remained plausible. James Webb now had the tools to decide between them. Its infrared sensitivity could detect the faint thermal glow of Earth-sized planets in habitable zone orbits. Its coronagraphs could suppress stellar glare enough to reveal companions hiding nearby, and its ability to map dust and debris could reconstruct the history of planet formation, even where planets themselves were absent. If worlds had formed and survived around Alpha Centauri A or B Webb should see the evidence. If they had not, the absence would speak just as clearly. The question was no longer whether these stars were calm enough, it was whether their gravitational relationship allowed worlds to exist at all. The answer would come not from chemistry or radiation, but from orbital mechanics. Binary stars do not merely share space, they reshape it. Alpha Centauri A and B orbit one another in a slow elongated dance ranging from roughly 11 to more than 30 astronomical units apart. On human timescales, the motion feels gentle. On planetary timescales, it is anything but. Gravity does not average out quietly. It accumulates. For any planet attempting to orbit one of these stars, the companion is never truly absent. Its gravitational pull rises and falls over decades, subtly altering the shape and orientation of planetary orbits. Small deviations become larger ones. Circular paths stretch into ellipses. Stable climates give way to extremes. Planet formation is especially vulnerable during its earlier stages. Worlds do not appear fully formed. They emerge gradually from disks of gas, dust, and ice that must remain calm long enough for particles to collide gently and stick together. This process requires millions of years of relative quiet. In the Alpha Centauri system, that quiet never existed. As the two stars sweep past one another, their combined gravity stirs the surrounding disks like a spoon through liquid. Particles that might otherwise drift peacefully are pulled onto crossing paths. Collision speeds increase. At low speeds, collisions build. At higher speeds, they destroy. Computer simulations of binary systems with separations like Alpha Centauri's converge on the same result. Material in the very regions where habitable planets would need to form experiences the strongest disruption. Too close to the star and temperatures are hostile. Too far away and material remains cold and sparse. The habitable zone sits in the middle, precisely where gravitational perturbations are most damaging. James Webb's observations confirmed what theory had long warned. Instead of dense structured disks capable of forming planets, the system shows only faint traces of debris. The signatures are not those of construction but of erosion, dust produced by grinding collisions, fragments left behind after larger bodies failed to survive. This is not a temporary condition. The binary orbit repeats endlessly. Every close approach reinforces the instability. Even if a planetary embryo managed to form briefly, it would be subjected to periodic disturbances strong enough to alter its orbit or shatter it outright. The problem is not that planets cannot exist around binary stars. Some binaries are close enough to behave like a single gravitational source. Others are wide enough that each star maintains its own calm domain. Alpha Centauri falls into neither category. Its configuration occupies a narrow but unforgiving range, close enough to interfere, far enough to prevent simplification. In this system, gravity does not provide a foundation, it provides a barrier. The failure to find stable planets around Alpha Centauri A and B is not surprising in retrospect. It is the expected outcome of a system whose architecture never allowed order to take hold. What appeared from Earth as two familiar suns turns out under closer inspection to be a dynamic environment where stability is the exception rather than the rule. And without stability, life never gets the time it needs to begin. James Webb did not need to see planets to understand what happened around Alpha Centauri A and B. The absence of worlds can be just as revealing as their presence. When stars form, they're surrounded by disks of gas and dust that carry the raw ingredients of planets. In young systems, these disks glow in infrared light as particles collide warm and gradually assemble into larger bodies. Over time, successful disks thin out as material is locked away into planets, leaving behind structured systems like our own. Round Alpha Centauri A and B Webb saw something very different. The infrared signatures revealed only a sparse debris disk, faint and irregular, containing less than a fraction of the material that once surrounded the young sun. The composition of this debris told a clear story. These were not the byproducts of gentle growth. They were the remnants of violent destruction. Dust grain showed size distributions consistent with high-velocity impacts. Instead of sticking together, particles had been shattered repeatedly, ground down into smaller and smaller fragments. Larger bodies, if they ever formed at all, did not survive long enough to shape the system. The environment favoured fragmentation, not accumulation. This outcome matches what simulations predict for binary stars with Alpha Centauri's separation. During close approaches, gravitational perturbations inject energy into the disk. Orbits become eccentric. Relative velocities rise. Collisions that would normally build planetary embryos instead pulverize them. The destruction unfolds slowly but relentlessly. Over millions of years, the disk loses its ability to create anything large. Over billions of years, radiation pressure and stellar winds remove the smallest fragments, entirely carrying them out of the system or into the stars themselves. What remains is not a nursery but a graveyard. Crucially, Webb's data shows that the inner regions of the system where habitable planets would need to exist are almost completely empty. The debris disk begins far beyond the zone where liquid water temperatures could occur. Inside that boundary there is little more than vacuum. This tells us that material was not merely rearranged. It was cleared out. Any rocky worlds that might have tried to form near Alpha Centauri A or B were either broken apart before they could grow, or scattered into unstable orbits that led to collision or ejection. The system did not fail late. It failed early during the brief window when planets must form. By the time the stars settled into their current rhythm, the opportunity was already gone. Planet formation is not a process that can be paused and restarted at will. It depends on conditions that exist only in the early life of a star. Once those conditions are disrupted, there is no second attempt. Alpha Centauri A and B did not lose their planets to later catastrophe. They never truly gained them in the first place. And with that realization, the last nearby hope for a habitable world quietly disappeared. Planet formation is not a flexible process. It does not adapt to hostile conditions or wait patiently for circumstances to improve. It operates within a narrow window governed by physics that allows construction only when relative calm exists. Round Alpha Centauri A and B, that window closed early. Once the primordial disks were disrupted, the system crossed a threshold from which it could not return. The debris left behind was not a reservoir waiting to rebuild. It was the residue of failure, small fragments moving too fast, colliding too violently, and losing energy in ways that favoured destruction rather than growth. James Webb's observations confirm that this environment has not softened with time. Collision velocities remain too high. Orbital eccentricities remain elevated. The gravitational influence of the binary pair continues to inject chaos into the system with every pass. Nothing in the data suggests a transition towards stability. Some hypotheses once proposed that planets might form late assembling slowly from leftover debris after the most violent interactions had passed. The physics does not support this hope. For particles to stick together, they must collide gently. At speeds of tens or hundreds of meters per second, even solid rock shatters. Webb's spectral measurements show exactly this regime in action. The debris disk around Alpha Centauri is dominated by fine dust produced by grinding collisions. This dust does not seed new worlds. It is the end state of repeated failure. Radiation pressure pushes it outward. Stellar winds strip it away. Over time, even the debris disappears. Without sufficient mass, there is no way to restart the process. Without calm, there is no way to maintain it. Planet formation is front-loaded. Success depends on getting it right early. Systems that fail during that initial phase do not recover billions of years later. They remain barren, not by chance, but by design. This distinction matters. It means Alpha Centauri is not a system that narrowly missed habitability. It is a system whose architecture made habitability effectively impossible from the beginning. The stars did not destroy worlds after they formed. They prevented worlds from forming at all. From a distance, Alpha Centauri appears mature and settled. From within, its history is written in absence. Empty regions where planets should be, cleared zones where material once circulated, a quiet that is not peaceful but final. The system offers no delayed opportunity, no late bloom, no hidden refuge waiting to be discovered. By the time humanity evolved and learned to look outward, the outcome had already been decided. The nearest stars were never candidates for life. They were evidence of how easily the conditions for life can fail to arise. When the Alpha Centauri system is considered as a whole, a clear pattern emerges. Each star eliminates habitability in a different way. Together they leave no refuge. Proxima Centauri destroys atmospheres through sustained stellar violence. Its planets are stripped, irradiated, and locked into thermal extremes. Alpha Centauri A and B are calmer stars, but their mutual gravity prevents planets from ever forming or surviving in stable life-supporting orbits. Where one star fails through radiation, the others fail through dynamics. This distinction matters because it removes coincidence from the explanation. Alpha Centauri is not unlucky in a single dimension. It is systematically hostile across all of them. In some systems, a red dwarf might be violent but isolated, allowing planets to form before losing their atmospheres. In others, binary stars might be disruptive but distant enough to leave stable zones untouched. Alpha Centauri offers neither escape. Its configuration closes every pathway simultaneously. The result is a stellar neighborhood with no safe harbor, no orbit where radiation is tolerable and gravity is stable, no region where atmospheres can persist and chemistry can evolve undisturbed. Each star enforces a different constraint, and those constraints overlap rather than compensate. This is why proximity becomes irrelevant. Alpha Centauri is close, bright, and familiar, but none of those traits translate into habitability. Distance from Earth does not correlate with suitability for life. Physical law does. James Webb did not reveal a system that narrowly missed success. It revealed one that never had a viable configuration to begin with. From its earliest history, the system evolved towards sterility not through catastrophe, but through ordinary processes acting exactly as expected. This realization reframes how astronomers interpret nearby stars. The nearest systems are not necessarily the most promising. They are simply the easiest to study. What Alpha Centauri shows is that accessibility does not imply opportunity. The system is not waiting to be explored. It has already delivered its verdict. 3 stars, 3 different mechanisms, 1 outcome. In the search for life beyond Earth, Alpha Centauri no longer represents a destination. It represents a constraint, a reminder that habitability is not distributed evenly, even among stars that seem familiar and close. And with that understanding, the implications begin to extend far beyond this single system, outward into the broader structure of the galaxy itself. Once Alpha Centauri was understood in full, its significance expanded beyond its own boundaries. The system stopped being a local disappointment and became a statistical warning. For decades, estimates of life in the Milky Way rested on an assumption of abundance. Hundreds of billions of stars implied billions of opportunities. Even if life emerged rarely, the sheer scale of the galaxy seemed to guarantee success somewhere nearby. Alpha Centauri was expected to confirm that intuition. Instead, it challenged it at the most fundamental level. The nearest stellar system contains 3 stars that together represent a large fraction of galactic reality. A red dwarf, the most common stellar type. 2 sun-like stars, the only class known to host life. If habitability fails across all 3, the failure cannot be dismissed as bad luck. It forces a reassessment of probabilities. Red dwarfs alone account for roughly 70% of all stars in the Milky Way. If their planets are systematically stripped of atmospheres and water, then most stellar systems are removed from consideration immediately. Of the remaining stars, a large fraction exist in binary or multiple configurations. Many of those binaries fall into separation ranges similar to Alpha Centauri A and B, where gravitational dynamics prevent stable planet formation in habitable zones. Each constraint narrows the field. Together they compress it dramatically. When these filters are applied, the optimistic numbers collapse. The galaxy does not lose a few marginal candidates. It loses entire categories. What remains is a smaller, quieter subset of stars with the right mass, the right isolation, the right formation history, and the right long-term stability. This shift is not philosophical. It is quantitative. Models that once predicted billions of potentially habitable worlds now yield far smaller values when constrained by observation. Millions instead of billions. Perhaps fewer. The exact number remains uncertain, but the direction of correction is no longer in doubt. Alpha Centauri delivers this message with unusual force precisely because of its proximity. If even the closest stars fail under scrutiny, then distance ceases to be the main obstacle in the search for life. The obstacle is rarity. The universe may be vast, but viable environments within it may be sparse. Life may not be scattered evenly across the galaxy, waiting to be discovered just beyond our reach. It may be confined to isolated oases separated by immense distances, both physical and statistical. The comforting idea that life should be common begins to erode under measured constraint. What replaces it is not despair but realism, a recognition that habitability is not a default outcome of planet formation, but a fragile convergence of conditions that rarely align. Alpha Centauri was close enough to test our assumptions. It was close enough to falsify them, and once those assumptions fell, a deeper question emerged. Not about where life might exist, but about why the galaxy appears so quiet. The silence, it seemed, might not be accidental. The silence that surrounds Earth has long been treated as a puzzle, a contradiction between expectation and observation. If the galaxy is vast and old, and if life arises easily, then intelligent civilization should be common. They should leave traces, signals, artifacts, something detectable across interstellar space. This tension became known as the Fermi paradox. Where is everyone? Alpha Centauri offers a sobering reframing of that question. The paradox assumes abundance. It assumes that habitable worlds are common enough for life to emerge repeatedly, and that intelligence follows often enough for civilizations to overlap in time and space. What James Webb has shown is that the first assumption may be deeply flawed. If habitable environments are rare rather than plentiful, then silence stops being surprising. Civilizations do not need to destroy themselves to explain the absence of signals. They may simply never arise nearby in the first place. The distances involved become decisive. A technological species separated by thousands of light years might as well not exist from our perspective. Communication across such gaps requires time spans longer than civilizations are likely to endure. Even radio signals traveling at the speed of light lose coherence over interstellar distances. They weaken, spread, and dissolve into cosmic noise. A message sent today might reach its destination after the sender has changed beyond recognition or vanished entirely. Dialogue becomes impossible. Detection becomes unlikely. Alpha Centauri once felt like a counterexample to this isolation, a nearby system that could in principle host life and perhaps even intelligence. Its failure removes that comfort. If the nearest stars are sterile, then the nearest inhabited systems, if they exist at all, may lie far beyond any practical horizon. The paradox begins to dissolve, not because intelligence is impossible, not because civilizations inevitably self-destruct, but because the environments required for life may be scattered sparsely across the galaxy. In that scenario, each inhabited world becomes an island. Consciousness arises in isolation, separated not only by distance but by time. Civilizations may flicker into existence and fade away, without ever knowing that others did the same elsewhere. The universe does not need to hide its inhabitants. It simply does not produce many of them. Alpha Centauri transforms the silence from a mystery into a consequence, a natural outcome of physics acting over billions of years. The galaxy may not be empty, but it may be quiet by necessity. And if that is true, then the most important conclusion is not about what we fail to hear. It is about what we already have, a single confirmed world where life endured long enough to become aware of the universe around it. Us. When the universe is viewed through this narrower lens, Earth begins to look different. Not ordinary, not interchangeable, but contingent in ways that are easy to overlook precisely because we live here. Our planet orbits a single stable star, not too massive, not too small. The sun's energy output changes over time, but slowly enough for atmospheres and oceans to adapt. Its magnetic activity is restrained compared to red dwarfs, and its habitable zone lies far enough out to avoid tidal locking and extreme radiation. Earth also arrived at this orbit under favourable circumstances. It formed in a disk that remained calm long enough for planets to assemble rather than shatter. Water-bearing material from the outer solar system was delivered instead of driven away. Volatiles accumulated rather than being stripped. An atmosphere formed and persisted. Just as importantly, Earth developed a strong magnetic field early in its history. That field deflected the solar wind, preventing catastrophic atmospheric loss. Beneath it, geological activity recycled carbon-regulated climate and replenished gases lost to space. Oceans buffered temperature swings. Chemistry was given time. Time is the unifying theme. Life on Earth did not appear quickly. Hundreds of millions of years passed before the first simple organisms emerged. Billions more were required before complex life evolved. Intelligence arrived only at the very end of that long experiment. At every stage, stability mattered more than abundance or proximity. None of these conditions were guaranteed. A slightly more active sun, a close stellar companion, a weaker magnetic field, a disrupted formation disk. Any one of these changes could have erased the path that led here. Alpha Centauri shows how easily that path can fail, not through exotic disasters, but through ordinary physics, acting in slightly different configurations. The difference between a living world and a dead one may hinge on details that appear minor until their consequences compound over billions of years. In that context, Earth is not just one habitable planet among many. It may be one of a small class of worlds where conditions aligned with unusual precision, a place where chemistry was allowed to persist long enough to become biology, and biology long enough to become awareness. This reframes humanity's position in the cosmos, not as conquerors destined to spread easily from star to star, but as custodians of something rare, a biosphere that survived filters most worlds never pass. If habitable planets are scarce, then there may be no nearby alternatives, no backup worlds waiting to be reached once technology improves. The assumption that we can always move on becomes fragile when the nearest stars offer nothing but sterility. Earth is not merely our home, it may be our only viable one for an unimaginably long time, and that realization carries consequences that extend far beyond astronomy. Alpha Centauri was never meant to be a destination. It only appeared that way from a distance. For decades, its proximity encouraged a quiet assumption that the universe would meet us halfway, that the first stars we reached would offer something familiar, something usable. A foothold beyond the sun, James Webb removed that assumption with measured clarity. What lies 4 light-years away is not promise. It is proof that habitability is not a reward for being nearby, proof that stars do not care about human timelines or aspirations, proof that the universe operates according to physical law, not narrative convenience. The nearest stellar system contains worlds that are stripped, irradiated, dynamically disrupted, or never formed at all. Not because something went wrong, but because everything behaved exactly as physics predicts. Radiation did what radiation does. Gravity did what gravity does. Time amplified both. Alpha Centauri does not mock the search for life. It instructs it. It tells us that optimism must be constrained by environment, not distance. That the path to life is narrow, fragile, and easy to miss. that the stars we hoped would welcome us first have nothing to offer but a lesson written in absence. This lesson reshapes the future. Interstellar exploration, if it ever happens, will not begin with the closest stars. It will begin with the rare ones. Systems farther away, quieter, more isolated, more stable. Targets that require patience measured in centuries rather than decades. The universe does not forbid life. It simply does not distribute it generously. And in recognizing that scarcity, something else comes into focus. Earth is not just where we happen to live. It is where an improbable sequence of conditions succeeded. A place that passed filters. Most worlds never encounter, let alone survive. The stars nearest to us are silent, not because the universe is empty, but because suitable homes are rare. The cosmic neighborhood is not hostile by intent. It is indifferent by design. Alpha Centauri stands as the clearest nearby example of that indifference. A system close enough to study in detail, yet utterly incapable of sustaining life. Not a failure of exploration, but a success of understanding. The search continues, not outward with blind hope, but forward with sharper constraints. And as we look farther into the galaxy, the message from our nearest stars remains unmistakable. If life is precious, it is because the universe makes it so difficult to keep. When we imagine life elsewhere in the universe, we often picture planets that almost made it, worlds that came close to becoming alive but failed because of bad luck. A violent star, a nearby supernova, a catastrophic impact. But that picture is misleading. Most planets do not fail late. They fail immediately, long before oceans could form, long before atmospheres could stabilize, long before chemistry could organize itself into anything resembling biology. The majority of worlds are already disqualified. Not by disaster, but by default. Planet formation is not a gentle process. It begins inside turbulent disks of gas and dust, where material collides at high speeds, fragments, reheats, and rearranges itself repeatedly. In these environments, nothing is optimized for life. The goal is not habitability. The goal is simply survival as a coherent object. From the moment a planet assembles, it faces a sequence of filters: size, composition, orbit, rotation, radiation, time. Each filter operates independently, and failure at any stage ends the story permanently. A planet that forms too small loses its atmosphere almost immediately. Gravity cannot hold on to gas once stellar radiation heats the upper layers. A planet that forms too large never becomes rocky at all. It inflates into a gas-dominated world with crushing pressures and no stable surface. Most planets fall into one of these two categories. Even among those that reach a narrow middle ground, new obstacles appear. Many never receive water. Others receive too much. Some lock into unstable orbits that drive extreme climate swings. Others rotate too slowly, too quickly, or not at all in ways that prevent long-term stability. And crucially, these failures are not rare exceptions. They are the dominant outcome. When astronomers detect exoplanets, the survivors bias our perception. We see the worlds that remain detectable, not the far larger population that never developed the properties we associate with habitability. For every planet that resembles Earth in size or temperature, countless others were eliminated earlier quietly and invisibly. Alpha Centauri showed us how a system can erase habitability through stellar violence and gravitational chaos. But even in calmer systems, even around gentle stars, most planets never reach the starting line. They are not dead worlds. They are precluded worlds. Understanding life in the universe, therefore, requires a shift in perspective. The question is not why so many planets are barren. The question is why any planet ever escapes these filters at all. Earth did. Not because it was destined to, but because it passed a sequence of improbable tests in the correct order over billions of years. This series is about those tests. The ones that quietly remove most worlds from consideration long before life has a chance to begin. To understand how rare living planets may be, we must first understand how efficiently the universe prevents them from ever existing. The first barrier to life appears before a planet even exists. Stars do not form alone. They are born inside dense clouds of gas and dust collapsing under gravity, fragmenting into multiple stellar embryos. Around these newborn stars, leftover material spreads into rotating disks. These protoplanetary disks are the raw environments from which planets must emerge. They are chaotic, violent places. Within the disk, dust grains collide at thousands of kilometers per hour. Shock waves heat material to extreme temperatures. Radiation from the young star ionizes gas and strips volatile compounds. Nothing about this environment resembles the calm stability we associate with habitability. Planets are not assembled carefully. They survive accidentally. Most solid material never becomes a planet at all. It spirals into the star, is blown away by stellar winds, or is shattered back into microscopic fragments during collisions. Only a small fraction manages to grow large enough to decouple from the gas and resist inward migration. Even among those survivors, outcomes diverge quickly. Some form too close to the star, where heat vaporizes water and drives off atmospheres before they can accumulate. Others form farther out, where ice dominates, composition locking planets into cold, volatile, rich states that never resemble Earth. Migration through the disk can drag planets inward or fling them outward unpredictably, often destabilizing entire systems. This process does not produce Earth-like worlds by default. It produces extremes. Rocky planets that form in the right region often experience violent late-stage impacts. These collisions determine core size, rotation rate, axial tilt, and internal structure. A slightly different impact history can erase a magnetic field, halt geological activity, or eject volatile inventories permanently. By the time a planet finishes forming, most of its fate is already sealed. If it lacks sufficient mass, its atmosphere will escape. If its core is poorly differentiated, it will never generate magnetic protection. If its orbit is eccentric, climate instability will dominate from the start. None of these failures require time. They happen immediately encoded into the planet's initial conditions. From a biological perspective, the universe has already done most of its filtering before chemistry even begins. The planets we later describe as potentially habitable are not typical products of formation. They are statistical survivors of a brutal selection process that favors nothing about life. This is why Earth's existence is not just rare, it is conditional. To understand habitability, we must abandon the idea that planets start neutral and later become hostile. Most planets are hostile from birth. They never cross into a state where life could plausibly begin, and the deeper we look into planet formation, the clearer this pattern becomes. Once a planet survives formation, it faces its first unforgiving constraint: size. Planetary mass is not a continuum of possibility. It is a narrow window bounded by failure on both sides. Too little mass and gravity cannot retain an atmosphere. Too much and the planet identifies as something else entirely. Small rocky worlds lose gas quickly. Stellar radiation heats their upper atmospheres, giving gas molecules enough energy to escape. This process begins immediately and never stops. Over time, even thick primordial atmospheres are eroded away. What remains is a barren surface exposed directly to space. Mars provides a familiar example. It likely formed with a denser atmosphere and surface water, but with only a fraction of Earth's mass, it could not hold onto that atmosphere once its magnetic field weakened. Over billions of years, the planet dried, cooled, and froze into the world we see today. Planets only slightly larger than Mars were a little better. On the other end of the scale, planets only a few times more massive than Earth cross a different threshold. Their gravity becomes strong enough to retain large amounts of hydrogen and helium from the protoplanetary disk. Instead of remaining rocky, they inflate into gas-rich worlds with thick envelopes and no solid surface. These are the so-called mini-Neptunes, one of the most common planet types detected by modern surveys. They are not failed Earths. They are a different outcome entirely. Between these extremes lies a narrow band where a planet can remain rocky, retain an atmosphere, and maintain pressures compatible with liquid water. That band is far thinner than early optimism assumed. Statistically, most planets do not land there. Exoplanet surveys reveal a clear pattern. There is a gap in planet sizes, sometimes called the radius valley, separating small airless worlds from larger gas-dominated ones. Earth sits near the lower edge of this valley, balanced precariously between atmospheric loss and runaway accumulation. A slight change in mass composition or formation timing could have pushed Earth into either category. This sensitivity matters because size influences everything else. Core pressure determines whether a magnetic field can form. Gravity controls atmospheric retention. Surface pressure regulates climate and chemistry. There is no correction later if size is wrong. Habitability does not emerge gradually as planets evolve. It is either possible from the beginning or it never is. Most planets fail this test silently. They do not lose life. They never acquire the conditions needed to attempt it. And even among those that pass further filters wait. Passing the size filter does not guarantee survival. It only allows the next test to begin. An atmosphere is not something a planet automatically keeps. It is something that must be defended continuously, often for billions of years, against forces that work relentlessly to remove it. Even planets with the right mass can lose their air if other conditions fail to align. Young stars are especially dangerous. In their early stages, stars emit intense ultraviolet and X-ray radiation while driving powerful stellar winds. This phase can last hundreds of millions of years, exactly when planetary atmospheres are most vulnerable. Gas in the upper atmosphere absorbs this energy, heats, expands and escapes into space. If this loss outpaces replenishment, the atmosphere thins and disappears. Earth survived this phase through a combination of timing and protection. Its atmosphere grew after the Sun's most violent youth had passed, and its magnetic field reduced the efficiency of atmospheric stripping. Many planets are not so fortunate. They form early close to active stars and lose their atmospheres before they can stabilize. Even later in a planet's life loss continues. Ultraviolet radiation breaks molecules apart. Hydrogen escapes easily, dragging heavier atoms with it. Stellar wind particles collide with atmospheric gas, transferring momentum and ejecting molecules into space. Without a strong magnetic field, these processes accelerate dramatically. Venus and Mars illustrate two different failures. Venus retained a thick atmosphere but lost its water, triggering a runaway greenhouse that sterilized the surface. Mars lost most of its atmosphere entirely, leaving behind a cold, desiccated desert. Both planets began with potential. Neither retained balance. Atmospheres must also be replenished. Volcanism releases gases from a planet's interior, rebuilding what is lost. But this requires active geology. A planet that cools too quickly or never develops sustained tectonic activity cannot replace escaping gas. Once atmospheric loss overtakes supply, the outcome is irreversible. This reveals a critical point. Atmospheric retention is not a one-time achievement. It is an ongoing negotiation between gravity, radiation, magnetic shielding, and geology. Failure in any one of these domains eventually ends the negotiation. Many planets never even enter it. They form with atmospheres that vanish quickly, or they retain atmospheres that become chemically hostile, or they lose the ability to replenish what space steadily removes. By the time surface conditions matter, the decision has already been made. From afar, these worlds may appear similar in size and temperature to Earth, but beneath that similarity lies a different history, one that quietly erased the possibility of life long before it could begin. And even an intact atmosphere is not enough, because stability over time matters more than presence at any single moment. Even with the right size and an atmosphere that survives its star's early violence, a planet still faces one of the most restrictive filters of all: water. Liquid water is often treated as a simple consequence of temperature. If a planet sits in the right orbital zone, water should exist. In reality, water must be delivered, retained, and protected. None of those steps are guaranteed. Most rocky planets form dry. Inside the inner regions of a protoplanetary disk, temperatures are too high for water ice to condense. The solid material that builds planets there is dominated by silicates and metals, not volatiles. Any water present during formation is typically bound into minerals or lost during energetic impacts. Earth's water did not originate where Earth formed. It arrived later delivered by water-bearing asteroids and possibly comets from colder regions farther out in the solar system. This delivery required precise timing. Too early, and water would have been lost during intense heating. Too late, and geological processes might not have integrated it effectively into the planet's surface and mantle. Many systems never experienced this delivery at all. Gravitational architectures often block inward transport of icy material. Giant planets can either shepherd water-rich bodies toward inner worlds or eject them entirely. A small change in the orbit of a massive planet can decide whether inner planets become oceans or deserts. Even when water arrives, keeping it is another challenge. Ultraviolet radiation breaks water molecules apart. Hydrogen escapes easily, especially from smaller planets or those lacking magnetic protection. Over time, oceans can be lost molecule by molecule, leaving behind oxygen that reacts with surface rocks or escapes as well. Mars likely followed this path. Geological evidence suggests it once hosted rivers, lakes, and perhaps shallow seas, but without sufficient gravity and magnetic shielding, its water inventory steadily declined. What remains today is locked-in ice and minerals inaccessible to life. Some planets face the opposite extreme. They accumulate so much water that continents never emerge. These water worlds may host deep global oceans hundreds of kilometers thick with immense pressure at the seafloor. Under such conditions, high-pressure ice forms, isolating liquid water from the rocky mantle below. Chemical exchange stops. Long-term climate regulation becomes impossible. Life requires more than water. It requires interaction, a balance between land and sea, between atmosphere and rock, between chemistry at the surface and chemistry below. Too little water fails that balance. Too much breaks it just as effectively. Water, like atmosphere and size, occupies a narrow window. Most planets miss it, and even those that succeed face another test, one that determines whether their climates can remain stable long enough for life to do anything with what it has been given. A planet can have the right size, retain an atmosphere, and possess liquid water, yet still fail for a quieter reason: instability. Life does not require perfection, but it does require consistency. Chemical evolution unfolds slowly through countless small interactions that must persist over immense spans of time. If a planet's climate swings too wildly, those processes reset faster than they can progress. Orbital dynamics are a primary source of instability. Many planets do not follow nearly circular orbits like Earth's. Even modest eccentricity can produce dramatic climate effects. When a planet moves closer to its star, temperatures spike. When it retreats, they plunge. Ice advances and retreats. Atmospheres expand and contract. Oceans partially freeze and evaporate in repeating cycles that stress any emerging chemistry. These cycles are not gentle seasons. They are global shocks. Axial tilt introduces another layer of risk. Earth's tilt is stabilized by the Moon, preventing chaotic variations over geological time. Without such stabilization, a planet's axis can wander unpredictably. Poles may swing toward the star. Equatorial regions may plunge into darkness. Climate zones migrate erratically across the surface. Models show that without a large moon, many Earth-sized planets experience extreme obliquity changes. Ice ages become permanent, or runaway heating sterilizes large regions. There is no stable baseline for ecosystems to adapt to. Rotation rate matters as well. Planets that rotate too slowly develop extreme day-night temperature differences. Atmospheric circulation struggles to redistribute heat. Weather patterns become violent and persistent. Planets that rotate too quickly experience intense jet streams and turbulent systems that can strip moisture from entire regions. Tidal interactions compound these effects. Worlds that orbit too close to their stars often become tidally locked. One hemisphere bakes under constant daylight. The other freezes in perpetual night. Even with an atmosphere, maintaining global habitability under such conditions is difficult. Without one, it is impossible. What emerges from these dynamics is a sobering picture. Climate stability is not the norm. It is an exception that arises only when orbital parameters rotation, axial tilt and system architecture align within narrow tolerances. Most planets fluctuate too much too fast or too often. Life does not need a calm world forever, but it needs one long enough. Earth's climate has changed sometimes dramatically, yet for billions of years those changes remained bounded. Oceans persisted, liquid water never vanished globally. Temperatures oscillated, but within limits that chemistry and biology could endure. That endurance is not guaranteed elsewhere. Many planets are not violently hostile. They are simply inconsistent. Their environments never settle into the long plateaus of stability that allow complexity to accumulate. And without those plateaus, time itself becomes an enemy rather than an ally. The next filter follows naturally from this one, because even a stable climate cannot persist without a deeper planetary engine working silently beneath the surface. Even a stable climate is only a surface illusion if nothing sustains it from below. Beneath every long-lived habitable world lies an internal engine, a slow circulation of heat, material and chemistry that operates far from view, yet determines whether surface conditions remain livable across billions of years. Without this engine, stability decays quietly, then collapses. On Earth, that engine is geology. Heat left over from formation combined with radioactive decay keeps Earth's interior active. The mantle convects, plates move, volcanoes erupt. This motion is not chaos. It is regulation. Carbon is buried, subducted, released and recycled through the atmosphere in a feedback loop that prevents runaway freezing or overheating. This process operates slowly. Precisely because it is slow, it works. Planets that cool too quickly lose this regulation early. Their interiors solidify. Plate tectonic stalls. Volcanism fades. Once that happens, atmospheric gases lost to space are no longer replaced. Carbon dioxide drawn down by weathering is never returned. Climate drifts toward irreversible extremes. Mars again offers a cautionary example. Geological evidence suggests it once possessed active volcanism and surface water, but its smaller size meant faster cooling. Its internal engine shut down early. Without tectonics, its atmosphere thinned. Without atmosphere, its climate collapsed. Larger planets are not immune. Some grow massive mantles but develop stagnant lids where the crust becomes too thick and rigid to recycle. Heat escapes inefficiently. Surface chemistry stagnates. Volcanism becomes episodic rather than continuous, producing violent bursts instead of steady regulation. In these worlds, climate stability is temporary. It may last tens or hundreds of millions of years, then fail. For life, that window may be far too short. Geology also governs nutrient cycling. Elements essential to life, carbon, phosphorus, sulfur, are released from rock through tectonics and weathering. Without continuous recycling, oceans and atmospheres become chemically exhausted. Even if life emerges, it cannot persist. This introduces another uncomfortable truth. Habitability is not only about conditions at the surface, it is about deep planetary structure, core size, mantle composition, heat flow, tectonic regime, factors determined early and rarely corrected later. A planet can appear promising from afar, Earth-sized, temperate, wet, yet lack the internal processes needed to sustain those conditions. From a distance it looks alive. From within it is already winding down. Earth's geological engine has operated for over 4 billion years. That endurance is not typical. It reflects a balance between size, composition and formation history that few planets achieve simultaneously. The surface may host life, but the planet must support it. And even this is still not enough, because life does not merely require a stable planet. It requires a stable star over a very specific span of time. All previous filters reduce possibility. This one defines inevitability. Life is slow, not metaphorically slow, but geologically slow. On Earth, the first chemical pathways toward biology likely began hundreds of millions of years after the planet formed. Simple single-celled organisms dominated for more than 3 billion years before complex life appeared. Intelligence emerged only in the final moments of that vast timeline. None of this could have happened quickly. Time is not a backdrop for habitability. It is an active requirement. A planet must remain stable not just briefly but continuously across spans that dwarf human history. Any interruption long enough to erase accumulated chemical complexity resets the process. Many planets never receive that uninterrupted interval. Stars change. Their luminosity increases. Their radiation environments evolve. Some become quieter with age. Others grow more violent. A planet that begins within a habitable range may drift out of it as stellar output rises. Water evaporates. Greenhouse feedbacks accelerate. A slow boil begins. This is not rare. It is expected. Low-mass stars burn gently but remain magnetically active for immense durations. High-mass stars stabilize quickly but die young. Only a narrow stellar class offers both longevity and restraint, and even then the timeline must align with planetary development. Planetary systems also evolve dynamically. Orbits shift. Resonances emerge. Distant companions perturb inner worlds over millions of years. A planet that begins in a stable configuration may become chaotic long after formation. Stability at the start does not guarantee stability over time. Impacts matter too. Large collisions decline as systems age, but they never vanish entirely. A single late impact can strip atmospheres, boil oceans, or tilt axes beyond recovery. Earth survived its bombardment phase early enough for recovery. Many planets do not. What makes time such a severe filter is that it compounds all others. A planet must be the right size for billions of years. It must retain atmosphere for billions of years. It must recycle carbon for billions of years. It must receive water and keep it for billions of years. It must orbit a stable star in a stable system for billions of years. Failure at any point ends the experiment. This is why habitability cannot be inferred from a snapshot. A planet that appears temperate today may have been frozen or scorched for most of its history. A world with water now may have lacked it during the crucial early window when life needed protection. Earth did not just become habitable, it stayed habitable. That persistence may be the most exceptional feature of all. When astronomers search for life, they often look for present conditions. But life is not produced by the present, it is produced by uninterrupted history. A long quiet stretch of planetary time during which chemistry was allowed to remember its previous steps. Most worlds never get that chance, and once this is understood, a final realization begins to take shape. Habitability is not a single hurdle but a narrowing corridor, and Earth sits improbably deep inside it. When all of these filters are placed end to end, a pattern becomes unavoidable. Habitability is not a wide landscape that planets occasionally wander into. It is a narrowing corridor. With each step forward, the walls close in. Fewer worlds remain. Fewer histories remain viable. Planet formation removes most candidates immediately. Size removes many of the survivors. Atmospheres eliminate more. Water reduces the field further. Climate instability removes nearly all that remain. Geology filters again. Time filters last. By the end, almost nothing is left. This is why the search for life often feels paradoxical. We discover thousands of planets, yet none clearly alive. The failure is not observational, it is structural. The universe produces planets efficiently, but habitable histories inefficiently. Each filter is blind. None of them are designed to exclude life. They operate according to physics that has no awareness of biology. Gravity does not care about atmospheres. Radiation does not care about chemistry. Orbital dynamics does not care about climate. Time does not care about complexity. Life must pass through all of them anyway. What makes this corridor so unforgiving is that success does not accumulate gradually. Passing one filter provides no protection against the next. A planet may clear 6 stages flawlessly and still fail at the 7th. There is no partial credit. Earth passed every filter in sequence, not because it was favoured, but because its history avoided disruption at each critical moment. When its star was violent, its atmosphere was forming. When impacts were common, its oceans could recover. When its interior began to cool, tectonics remained active. When climate oscillated, feedbacks prevented collapse. None of this was guaranteed. If Earth's formation had occurred a little closer to the Sun, water would have been lost. A little farther, ice might never have melted. A slightly smaller core, no magnetic field. A slightly larger planet, a gas envelope. A slightly different orbit, chaotic climate. Each alternative was plausible. Most occurred elsewhere. From this perspective, Earth is not the standard by which planets should be judged. It is the outlier, the rare case where the corridor remained open long enough for life to pass all the way through. This reframes the meaning of Earth-like. Similarity in size or temperature is superficial. What matters is similarity in history, a matching sequence of survival across billions of years under constraints that are usually fatal. When astronomers say that a planet could be habitable, they often mean that it has not yet been ruled out. But the corridor teaches a harsher lesson. Not being ruled out is not the same as being likely. Most worlds are eliminated quietly, long before we ever see them, and as the corridor narrows toward its end, a deeper implication emerges, one that does not concern planets at all, but the role of observers within the universe that produced them. As the corridor narrows, another distortion becomes visible, not in the universe itself, but in how we observe it. We do not see most planets. We see the survivors. Modern astronomy is extraordinarily powerful, but it is not neutral. Detection methods favour large planets close to their stars, worlds with thick atmospheres, systems that remain dynamically loud and observable. The planets easiest to find are not the planets most likely to host life. This creates a profound survivorship bias. We catalogue what remains detectable, not what failed early. Airless worlds leave little signature. Planets that lost their atmospheres long ago blend into stellar noise. Systems that never assembled stable inner planets produce nothing for our instruments to measure. From our perspective, these worlds barely exist. As a result, the exoplanet census overrepresents planets that pass certain filters while underrepresenting those eliminated quietly. Gas-rich worlds dominate catalogues because they are easy to see. Compact systems appear common because their transits repeat frequently. None of this reflects habitability. It reflects visibility. Earth would be difficult to detect from afar. Its atmosphere is thin compared to gas planets. Its orbit is wide enough to produce rare transits. Its signal would be subtle, easily lost unless observed deliberately. If Earth orbited another star, it might already exist in someone else's data unnoticed. This bias matters because it shapes expectations. When we see many planets, we intuit abundance. But abundance of planets does not imply abundance of viable histories. The corridor does not care how many attempts are made. It only cares how many survive the entire sequence. From inside the corridor, success looks inevitable. From outside, it is almost invisible. This is the same illusion that affects observers everywhere. Survivors infer normality from survival, but survival itself is evidence of rarity. Earth feels typical because we are here, but its continued existence is the result of filters most worlds never pass. Correcting for this bias changes the interpretation of every new discovery. A planet detected in the habitable zone is not a candidate for life. It is a question mark, one that must survive an entire unseen history before biology becomes plausible. The deeper we look, the more the search shifts from counting planets to reconstructing timelines, from snapshots to stories, from where a planet is now to how it managed to get there without being erased. And as that realization settles, the corridor reaches its final implication, not about where life might exist, but about why observers exist at all. At the end of the corridor, a subtle but powerful implication appears. The universe does not merely filter planets, it filters observers. Every intelligent species capable of asking questions about the cosmos must arise on a world that passed every previous constraint. Size, atmosphere, water, climate, geology, time. None can fail. Only then does biology persist long enough for minds to emerge that can reflect on their own improbability. This creates a profound asymmetry. Most planets never host life. Most life never becomes complex. Most complex life never becomes intelligent. And most intelligent life, if it exists elsewhere, emerges on worlds that look ordinary only because they survived. From inside such a world, survival feels normal. The environment appears stable. The sky seems calm. The long chain of contingencies that made observation possible fades into the background. Observers experience the end state, not the narrow path that led there. This is not a philosophical trick. It is a selection effect imposed by physics. Any observer who exists must exist somewhere that allowed observation to occur. Worlds that failed leave no witnesses. The universe, therefore, appears more hospitable than it truly is, simply because hostile histories erase their own evidence. This insight reframes how rarity should be interpreted. If observers are rare, then every observation is already conditioned on extraordinary success. The fact that we find ourselves on a planet that remained habitable for billions of years does not imply that such planets are common. It implies that no observation could occur anywhere else. Earth does not testify to abundance. It testifies to survival. When astronomers ask how typical our planet is, the answer depends on perspective. From the outside, Earth is an outlier. From the inside, it is the only place where the question could be asked. Both statements are true simultaneously. This resolves a long-standing tension in astrobiology. The universe can be vast, old and rich in planets, yet still quiet. Not because life is forbidden, but because the conditions that permit long-term observers are stacked against it. The corridor does not end with life. It ends with awareness, and awareness does not spread easily. It emerges late precariously on worlds that avoided failure long enough to remember their own past. This understanding does not diminish humanity's significance. It sharpens it. It suggests that consciousness is not an expected outcome of cosmic evolution, but a rare byproduct of stability sustained against overwhelming odds. And with that realization, the script approaches its final question. Not where life might exist next, but what responsibility accompanies existence at all. Once survival is understood as improbable, continuation becomes meaningful. A living world is not just a place where life began. It is a place where failure did not arrive in time. Every additional year of habitability represents a quiet victory over processes that usually prevail. Radiation did not strip the air. Geology did not stall too early. Climate did not collapse into extremes. Time passed without erasing complexity. On Earth, this continuation has now crossed a new threshold. For the first time, a biosphere has produced a species capable of understanding the conditions that made it possible. That awareness changes the equation. Until now, habitability was passive, maintained by planetary processes indifferent to outcomes. From this point forward, it is no longer indifferent. Intelligent life introduces feedback. Human activity now influences atmospheric composition, climate balance and biospheric stability on timescales far shorter than geological ones. Processes that once operated slowly are being overridden quickly. For the first time, the continuation of a habitable world depends not only on planetary physics, but on choices made by the life it supports. This is unprecedented. Every previous filter was external. This one is internal. A planet that survived billions of years of cosmic hazards now faces a new variable. Whether its observers can avoid becoming its destabilizers, the corridor that filtered planets into silence now narrows further, testing not geology or orbit, but behavior. If habitable worlds are rare, then losing one is not a local tragedy. It is a cosmological one. A failure that removes an entire branch of possible observation from the universe. When a biosphere collapses, the universe loses not just life, but a way of knowing itself. This is not a moral claim, it is a physical consequence. The same indifference that made habitability difficult will not intervene to preserve it. Stars will continue to shine. Galaxies will evolve. Physics will proceed unchanged. Only one thing is fragile in that picture: sustained awareness. Alpha Centauri showed us how easily planets fail without intention. This series has shown how many ways failure can occur before life ever begins. Earth demonstrates that success is possible but not durable by default. Continuation must now be active. The rarest resource in the universe may not be energy, matter, or even time. It may be uninterrupted habitability guided by understanding. A world that not only survives but knows why it survived and chooses not to undo it. With that realization, the corridor reaches its end. Not in certainty but in responsibility. The corridor ends here, not with a discovery but with a boundary. The universe does not guarantee second attempts. It does not preserve habitable worlds once they fail. It does not compensate for lost atmospheres, vanished oceans, or destabilized climates. When a planet leaves the narrow corridor of habitability, physics does not guide it back. Alpha Centauri makes this clear. Those worlds did not fall from grace. They followed the most common outcome. Sterility is not an accident in the cosmos. It is the default. Earth is different only because it endured. For billions of years it remained inside a narrow band of conditions where chemistry could remember itself, where biology could accumulate complexity, where ecosystems could recover from shocks rather than collapse. That endurance was never promised. It was not written into the laws of nature. It emerged from a sequence of contingencies that happened to align. Nothing in astrophysics suggests that such alignment will occur nearby again. Nothing in planetary science implies that another Earth awaits us within easy reach. The nearest stars have already shown us what failure looks like. Not dramatic but thorough. This reframes the future. Interstellar travel does not offer an escape from planetary responsibility. Migration is not a fallback plan when environments degrade. The corridor that allowed life to emerge here does not repeat on demand elsewhere. It closes far more often than it opens. The universe is vast, but viable worlds are not evenly distributed within it. They are isolated outcomes separated by immense distances and long spans of time. If others exist, they are likely too far to reach, too distant to help, too remote to replace what is lost here. This does not make Earth unique in a mystical sense. It makes Earth fragile in a physical one. A habitable planet is not a stage waiting for actors. It is a dynamic system that can fall silent permanently. When that happens, the universe does not notice, but the silence is real. The search for life beyond Earth will continue. It should. Knowledge is never wasted, but Alpha Centauri and every filter that followed it deliver a clear message. The continuation of life we already know may be the most consequential scientific problem humanity will ever face. Because once the corridor closes, it does not reopen. Earth passed the filters. Earth reached awareness. What happens next is not determined by stars or orbits or radiation. It is determined here. If most worlds fail, not because of catastrophe but because stability is rare, then the question changes. The search for life is no longer about proximity or abundance, or even planets that look familiar at a glance. It becomes a problem of patience, of identifying stars that remain calm long enough, systems that evolve slowly enough, and environments that resist disruption rather than invite it. Alpha Centauri showed us where life cannot survive. The filters showed us why most worlds never try. The next step is not to ask whether life exists elsewhere, but where the universe allows it to endure. To find those places, we must stop looking at the brightest stars and start listening for the quiet ones. After Alpha Centauri, the universe feels quieter for a reason. Not empty, selective. When astronomers first mapped the nearby stars, proximity seemed like an advantage. The closer a system was, the easier it would be to study. The easier it would be to reach. The easier it would be to imagine life taking hold. Alpha Centauri embodied that intuition. 3 stars close enough to matter, familiar enough to inspire hope. James Webb showed us that proximity was never the point. What matters is not how near a star is, but how it behaves over time. Whether it flares violently or settles into restraint. Whether it lives loudly or quietly. Whether it allows its planets to accumulate history without erasing it. Silence, it turns out, is not absence. It is information. Stars broadcast their character continuously, through radiation, through stellar winds, through magnetic storms that reach far beyond their surfaces. Most stars announce themselves with violence, especially early in their lives. They burn hot flare often and reshape the environments around them long before planets have a chance to stabilize. Life cannot negotiate with that. The worlds that endure are not those bathed in abundance, but those sheltered by consistency. Planets that orbit stars, which change slowly, flare rarely and provide energy without chaos. These stars are not the brightest. They are not the most dramatic. They do not dominate the night sky. They are easy to overlook. In the search for life, this creates a reversal of instinct. The systems most likely to host long-lived biospheres are not those that draw attention, but those that barely register. Stars that burn steadily rather than spectacularly. Systems that evolve quietly rather than dynamically. The universe is full of light. Habitability prefers restraint. This is why the next phase of the search cannot begin with planets at all. It must begin with stars, with identifying which stellar histories allow planetary histories to persist without interruption, with separating stars that merely shine from stars that endure. The question is no longer which planets are warm enough. It is which stars are calm enough. Somewhere among the countless points of light are stars that have spent billions of years doing almost nothing remarkable. No extreme flares, no violent winds, no sudden shifts in output. Just steady fusion, slow evolution, and long stretches of predictability. If life exists elsewhere in the galaxy, it is likely orbiting one of these quiet suns. To find them, we must learn to value what the universe does not shout. At first glance, stars seem simple. They shine, they burn fuel, they age. But beneath that simplicity lies a crucial distinction that reshapes the search for life. Stars do not mature uniformly. Some calm down with time. Others never do. Early in their lives, nearly all stars are violent. Magnetic fields twist, surfaces erupt, radiation surges outward in flares that can dwarf anything the modern sun produces. For young planetary systems, this phase is often decisive. Atmospheres are stripped, water is lost, orbits are destabilized. What matters is what happens next. Sun-like stars gradually settle. Their magnetic activity weakens, flare frequency declines, radiation output becomes predictable on geological timescales. By the time planets have cooled, oceans have condensed, and atmospheres have thickened, the star has learned restraint. This transition is not guaranteed across stellar types. Red dwarfs, despite their small size and low luminosity, remain magnetically active for billions, sometimes trillions of years. Their interiors are fully convective, constantly churning magnetic fields that never truly relax. For planets in close orbits, this means endless exposure to flares, winds and radiation long after formation. Massive stars fail in the opposite direction. They stabilize quickly but burn through their fuel rapidly. Their lifetimes are measured in millions, not billions of years. They explode or fade before life has time to move beyond chemistry. A planet around such a star may enjoy calm conditions briefly, but the clock runs out too soon. Between these extremes lies a narrow stellar middle ground. Stars with enough mass to settle, but not so much that they rush toward death. Stars that reduce their magnetic violence early and then remain stable for billions of years. Stars that provide energy without interruption and time without threat. These stars do not dominate the galaxy, but they matter disproportionately. The search for life, therefore, becomes a question of stellar biography rather than brightness. Not how luminous a star is today, but how it behaved across its entire history. Did it flare aggressively during the period when atmospheres were vulnerable? Did it calm down before water was lost? Did it remain predictable long enough for biology to compound complexity? A star's past is often more important than its present. Two stars may look similar now, yet have shaped their planets in radically different ways. One may have erased early habitability through prolonged violence. The other may have stepped back just in time. The quiet stars are not silent by chance. They are quiet because their internal physics allows them to be, and thus differences written deep inside stellar interiors may determine where life is even possible to begin. Among the vast diversity of stars, one group has quietly moved to the center of astrobiological attention. Not the red dwarfs that dominate the galaxy, not the bright yellow stars that resemble our Sun, but the stars in between. These are K-type stars, often called orange dwarfs. They are smaller and cooler than the Sun, but larger and more stable than red dwarfs. Their light is gentler. Their habitable zones lie farther out relative to stellar size, reducing tidal locking and radiation exposure. Most importantly, their magnetic activity declines earlier and remains subdued for much longer. In cosmic terms, they age gracefully. Orange dwarfs burn their fuel slowly, granting them lifetimes measured not in billions but tens of billions of years. Yet unlike red dwarfs, they do not remain magnetically violent throughout that time. After an early active phase, many settle into long epochs of relative calm. This combination is rare. A long-lived star that becomes quiet early offers something extraordinary. Time without punishment. Planets in its habitable zone can retain atmospheres, preserve water, and avoid the constant reset imposed by flares and stellar winds. From a biological perspective, this is ideal. Life does not need abundant energy. It needs reliable energy. Photosynthesis adapts easily to lower light levels given stability. What it cannot adapt to is unpredictability that repeatedly destroys complex molecules and erases environmental memory. Orange dwarfs provide consistency. Their habitable zones are also wide enough to reduce orbital fragility. Planets can orbit without becoming tidally locked. Seasonal cycles can exist without extreme contrast. Climate regulation becomes possible without requiring perfect tuning. None of this guarantees life, but it removes several of the most common failure modes seen elsewhere. Statistically, orange dwarfs are less common than red dwarfs, but far more numerous than Sun-like stars. This places them in a favourable position. They are common enough to matter, but not so common that their internal physics works against habitability. If life exists elsewhere in the Milky Way, it may not orbit stars like our Sun, and it almost certainly does not orbit stars like Proxima Centauri. It may instead circle these quieter, dimmer suns overlooked not because they are unimportant, but because they are unremarkable. The irony is sharp. The stars most likely to host life are not the ones that command attention. They are the ones that simply persist steadily and quietly for billions of years. To find them, astronomers must change what they prioritize. Not brilliance, not proximity, but restraint. And once that shift is made, another layer of complexity appears. Because even a quiet star is not enough. Its planets must also be allowed to remain alone. Even the calmest star can fail its planets if it does not stand alone. Stars rarely form in isolation. Most are born in clusters accompanied by siblings that linger nearby or remain gravitationally bound. Binary and multiple star systems are common across the galaxy. From a distance, this companionship seems harmless. From the perspective of habitability, it is often decisive. Gravity does not share gently. When two stars orbit each other, their combined gravitational field reshapes everything around them. Planet-forming disks are truncated, stirred and destabilized. Material that might otherwise settle into orderly orbits is stretched, scattered, or driven into destructive collisions. The regions where temperate planets could form are often the most affected. Alpha Centauri demonstrated this clearly. Its stars are individually suitable yet collectively hostile. The binary interaction erased stable planetary pathways long before habitability could even be tested. This pattern repeats elsewhere. Many binary systems occupy separations that maximize disruption, rather than minimize it. Solitary stars avoid this problem entirely. Around a single star, planetary disks can extend smoothly. Orbits can circularize. Resonances settle rather than amplify. The long-term evolution of planets becomes predictable rather than chaotic. This predictability is not cosmetic. It is foundational. Life requires continuity. In multi-star systems, even planets that form successfully face long-term risks. Companion stars periodically perturb orbits, increasing eccentricity over millions of years. A planet may begin in a stable habitable zone and slowly drift into extremes. Climate destabilizes not suddenly but inexorably. Solitary stars provide insulation against this fate. They allow planetary systems to evolve quietly without external gravitational interference. Giant planets can occupy stable positions that protect inner worlds rather than destabilize them. Small variations dampen over time instead of escalating. This does not mean binary systems can never host planets. They can, but the configurations that allow long-term habitability are rare, tightly constrained, and easily disrupted. By contrast, single-star systems offer wide margins for stability. From a statistical standpoint, this matters enormously. Roughly half of Sun-like stars exist in binary or multiple systems. Eliminating those systems from consideration immediately halves the field. The remaining solitary stars become disproportionately important, not because they are special, but because they are permissive. When combined with stellar type, the picture sharpens further. A quiet orange dwarf that lives alone occupies a privileged region of possibility space. It minimizes radiation hazards. It minimizes gravitational chaos. It maximizes uninterrupted time. None of this guarantees life, but it defines where life is least likely to be erased. The search for habitable worlds therefore converges on a specific architectural preference. Calm stars, solitary systems, planets allowed to grow, settle, and persist without interference. In the universe, solitude is not loneliness, it is protection. And once this is understood, the search must widen again, not outward in distance, but inward into the structure of entire stellar neighborhoods. Even around a quiet solitary star, habitability is not decided by the planet alone. Planets do not exist in isolation. They share their system with other worlds, and those neighbors quietly shape their fate. Some companions protect, others destabilize. The difference can determine whether a habitable planet remains intact long enough for life to matter. In our own solar system, this role is easy to overlook because it is subtle. Jupiter, for example, is often described as a shield. Its immense gravity deflects or captures many comets and asteroids that might otherwise strike Earth. The reality is more complex, but the principle holds. Large outer planets influence the flow of debris through a system shaping impact rates over billions of years. Too many impacts and habitability resets repeatedly. Too few and essential materials may never arrive. Giant planets also sculpt orbital architecture. Their positions determine whether inner worlds remain on stable, nearly circular orbits, or are driven into eccentric paths that destabilize climate. A giant planet that migrates inward can destroy entire inner systems. One that forms and stays far out can act as a stabilizing anchor. Timing is critical. If giant planets migrate early, they erase potential habitable worlds before they fully form. If they migrate late, they can destabilize mature planets long after life might have begun. Only a narrow set of histories produces long-term calm. Smaller companions matter as well. Moons can stabilize axial tilt, moderating climate over geological timescales. Earth's moon prevents chaotic swings that would otherwise drive extreme climate variation. Many planets lack such stabilization, leaving their climates vulnerable to slow, destructive oscillations. Even asteroid belts play a role. A belt that is too massive produces frequent catastrophic impacts. One that is too sparse delivers little water and few complex molecules. The location and mass of these belts are determined by the positions of giant planets early in system history. Once set, they remain largely fixed. What emerges is a systems-level requirement. Habitability is not a property of a planet, it is a property of an arrangement. A quiet star may provide the right energy. A solitary system may provide stability, but without the right planetary companions in the right places, the corridor still closes. Too much chaos or too little interaction, and the conditions that allow life to persist disappear. This further narrows the search. Stars must be calm, Systems must be solitary. Architectures must be balanced. Each requirement removes vast numbers of candidates, and yet the universe is large enough that some systems do pass all of them. They are simply harder to find, quieter and less conspicuous than we once expected. The closer astronomers look, the clearer the pattern becomes. Life-friendly systems are not dramatic. They are restrained, carefully arranged, and above all rare. And with that understanding, the search moves from stars and systems to an even larger scale, because where a system lives in the galaxy may matter just as much as how it is built. Even a perfectly calm star surrounded by a well-balanced planetary system can still fail if it resides in the wrong part of the galaxy. The Milky Way is not uniform. Its environment changes dramatically with location. Density, radiation, and chemical history vary from one region to another, shaping planetary systems long before life has a chance to emerge. Near the galactic center, stars crowd together. Supernovae occur more frequently. High-energy radiation floods interstellar space. Gravitational interactions are common. Planetary systems are exposed to forces that can strip atmospheres, disrupt orbits, or sterilize surfaces outright. These regions are rich in heavy elements, but they are hostile. Farther out near the edges of the galaxy, a different problem appears. Metallicity drops. There are fewer heavy elements available to form rocky planets' cores and magnetic fields. Worlds that form here are often small, volatile, poor, or structurally incomplete. Stability may exist, but the raw materials for life do not. Between these extremes lies a narrow band often called the galactic habitable zone. This region is far enough from the galactic center to avoid frequent radiation catastrophes, yet close enough to benefit from generations of stellar enrichment. Heavy elements are abundant. Supernovae are rare enough to allow long periods of uninterrupted planetary history. Orbital environments are comparatively calm. Our Sun resides within this band. This is not coincidence. It is another filter. Stars do not choose where they form. Their birthplaces are determined by the structure and evolution of the galaxy itself. Many stars begin life in regions that doom their planets before they form. Others migrate over time, drifting into or out of safer zones. Only a fraction remain in favorable neighborhoods long enough for habitability to persist. This adds another constraint to the search. A quiet star is not enough. A stable system is not enough. Even a well-timed planetary architecture is not enough. The broader galactic environment must also cooperate. From this perspective, habitability is not merely planetary or stellar, it is galactic, a product of location, timing, and history on scales far larger than any single system. The stars most likely to host life are not only calm and solitary, they're also residents of quiet galactic suburbs, regions where catastrophe is rare, enrichment is sufficient, and time can accumulate without interruption. As astronomers widen their search, this realization reshapes priorities once again. Not all quiet stars are equal. Some are simply quiet in dangerous places. The truly promising targets are quiet in quiet neighborhoods. And once those neighborhoods are identified, the search narrows to its final practical challenge. Because even if such stars exist, even if such systems formed, we must still be able to recognize them. And that may be the hardest part of all. Once the requirements are assembled, calm stars, solitary systems, balanced architectures, quiet galactic neighborhoods, an uncomfortable conclusion follows. Our search strategy has been misaligned from the beginning. Astronomy favors what is easy to detect: bright stars, large planets, tight orbits, dramatic signals that repeat quickly and stand out against noise. These priorities are logical for discovery, but they are poorly matched to habitability. Life-friendly systems do not announce themselves. Planets that orbit far enough out to avoid tidal locking transit infrequently. Their signals are weak and easy to miss. Thin atmospheres produce subtle spectral features that demand long observation times. Quiet stars lack the dramatic variability that draws attention in surveys. In other words, the systems most likely to support life are the least likely to be noticed by accident. This creates a systematic blind spot. Exoplanet catalogues are dominated by hot planets close to their stars, gas-rich worlds with thick atmospheres and compact systems where multiple planets orbit in tight resonances. These configurations are fascinating from a dynamical perspective, but they are often hostile to long-term biological stability. We have been counting what shouts, not what whispers. Even when potentially habitable planets are identified, they are often flagged based on present-day conditions alone. Temperature, size, distance from the star. What is usually missing is the deeper question of history. Did the star flare violently for billions of years? Did the planet lose and regrow its atmosphere? Did its orbit remain stable, or did it wander through extremes? These questions are harder to answer, and so they are often deferred. But habitability is not about where a planet is now. It is about whether it avoided erasure long enough for life to matter. That history is invisible in a single transit curve or spectral snapshot. It must be reconstructed indirectly, patiently, and often statistically. This implies that many truly promising systems may already exist in our data unrecognized. They do not stand out. They do not repeat often. They do not produce dramatic signatures. They require deliberate attention rather than automated discovery. Future searches will need to invert their logic. Instead of starting with planets and asking whether they could host life, astronomers may need to start with stars. Identify those with long, quiet histories, then ask whether they host planets at all. Many will not, but the few that do may represent the highest value targets in the galaxy. The search for life is therefore becoming less like a census and more like an investigation. Fewer candidates, more scrutiny, longer timelines, and this shift carries a final implication. If life-friendly systems are quiet, rare, and difficult to detect, then the universe may not feel empty because it lacks life. It may feel empty because we have been listening for the wrong kind of signal. The quiet stars do not call out, they wait. Recognizing quiet stars introduces a new challenge, one that has nothing to do with physics and everything to do with time. The systems most likely to host life are not only subtle, they are slow. A planet orbiting a calm solitary star at a comfortable distance may take years to complete a single orbit. Its transits are rare, its atmospheric signals are faint. Detecting it requires repeated observations across long intervals, sometimes decades. Confirmation is not a matter of discovery, but of persistence. Modern astronomy is not optimized for this. Most surveys are designed around efficiency. They scan large regions of the sky looking for frequent repeatable signals that can be confirmed quickly. This approach is ideal for finding close-in planets and dynamic systems. It is poorly suited to finding the kinds of worlds that remain stable for billions of years. Life favors patience. Detection often does not. Quiet stars demand long baselines. Their activity cycles unfold slowly. Their planets reveal themselves gradually. Subtle trends matter more than dramatic events. A single dataset is rarely enough. Meaning emerges only when observations accumulate over time. This creates a structural mismatch between habitability and discovery. The most promising targets require missions that last longer than typical funding cycles. They require instruments calibrated for stability rather than speed. They require researchers willing to commit to questions whose answers may arrive years after the initial observation. In other words, they require a different scientific culture. The irony is difficult to ignore. To find worlds where life had enough time to evolve, we must be willing to give our searchers enough time to succeed. The universe does not reward haste when it comes to habitability. It rewards endurance. Some of the most promising systems may not even reveal planets directly. Instead, they may reveal absence, quiet debris disks, stable stellar outputs, chemical compositions that suggest calm formation histories. These indirect clues are easy to overlook, yet they may be the strongest indicators that a system has avoided early catastrophe. James Webb has begun to shift this balance. Its ability to study stars over long periods, to characterize atmospheres subtly, and to observe faint systems deliberately marks a transition. But Webb is only the beginning. Future observatories will need to embrace patience as a design principle. They must trade speed for depth, coverage for continuity, breadth for history, because the quiet stars do not yield their secrets quickly. They ask a simple question in return: are we willing to wait long enough to hear them? When patience is accepted as a requirement, habitability stops being a property and becomes a timeline. A life-friendly system is not defined by a moment when conditions look right. It is defined by how long those conditions remain uninterrupted. This shifts the entire framework of the search. Instead of asking whether a planet can host life, the more relevant question becomes whether it has avoided interruption long enough for life to matter. From this perspective, the universe looks different. Most stars shine for billions of years, but only a subset do so without prolonged violence. Most planets orbit stably for long stretches, but only a few avoid slow dynamical drift. Most atmospheres form, but fewer persist. Each of these processes unfolds gradually, often invisibly, until a threshold is crossed and recovery becomes impossible. Habitability is therefore not fragile in the short term. It is fragile cumulatively. A planet does not usually fail because of a single catastrophic event. It fails because small instabilities accumulate without correction. Slight increases in stellar output, minor orbital perturbations, gradual atmospheric thinning. Each change seems tolerable on its own. Together over millions of years they close the corridor. This is why snapshots mislead. A planet observed today within a habitable temperature range may be uninhabitable in a deeper sense. Its past may include long frozen epochs, or extended runaway greenhouse phases that erased early chemistry. Or its future may already be constrained by trends that have not yet crossed visible thresholds. True habitability exists only when the past, present, and near future align. Quiet stars matter not because they are gentle today, but because they were gentle when it mattered most, and are likely to remain so long enough for complexity to accumulate. Their value lies in continuity. This continuity also reframes the timeline of life. If habitable environments are rare and slow to assemble, then life elsewhere may not be ancient or ubiquitous. It may be emerging now or may emerge far in the future, long after short-lived stars have burned out and violent regions have quieted. The galaxy's capacity for life may increase with time, not decrease. In that scenario, humanity may not be late. It may be early. The quiet stars that can host life may simply not have had enough uninterrupted time yet. Their planets may still be accumulating chemistry, stabilizing climates, and settling into the long plateaus required for biology to begin. If so, the silence we observe is not emptiness. It is incompletion, and this leads naturally to the final phase of the search. Not just identifying where life could exist, but understanding what our moment in cosmic time allows us to witness. Because the quiet stars are not only quiet in space, they may also be quiet in time. When quiet stars are placed on a galactic timeline, a counterintuitive possibility emerges. The universe may not be empty. It may be unfinished. Stars like orange dwarfs live far longer than the current age of the universe. Many will remain stable for tens of billions of years beyond the present era. Their planets, if properly configured, may enjoy uninterrupted habitability for spans far exceeding Earth's history. In cosmic terms, these systems are just getting started. Life as we know it requires time to accumulate complexity. Billions of years are not an anomaly. They are a baseline. If the most stable stellar environments have only recently become calm enough to permit long-term habitability, then the emergence of observers may be biased toward the future rather than the past. This reframes the familiar question. Instead of asking why we do not see ancient civilizations everywhere, we might ask whether the conditions that allow civilizations to persist have only recently become widespread. The galaxy's early epochs were more violent, supernovae were frequent, radiation levels were higher, chemical enrichment was incomplete, stability was rare, only later did calm regions expand. In that context, Earth may not be typical in age, but in timing. A world that reached habitability just as the galaxy began to quiet. A planet that found itself in a rare corridor of stability at a moment when those corridors were still uncommon but growing. This possibility weakens one of the strongest intuitions behind the search for extraterrestrial intelligence. The idea that civilization should be far older and far more advanced assumes that habitability was available early and often. If it was not, then intelligence may be sparse, not because it fails, but because it has not yet had time to appear widely. The silence then is not evidence of absence, it is evidence of sequence. Life may be distributed unevenly in time as well as space. Worlds that will host biospheres in the distant future may currently appear barren. Their stars may already be calm, their systems stable, but their planets are still traversing the long chemical path that precedes biology. If that is true, then humanity occupies a narrow observational window, early enough to see the galaxy before it fills with life, late enough to recognize what conditions make life possible at all. This does not place us at the center of anything. It places us at an inflection point, and that inflection point carries a final implication, one that closes the arc of this series not with speculation but with constraint. Because if life is rare, quiet and slow to emerge, then the most important signal in the universe may not be something we receive, it may be something we preserve. The search began by looking outward. It ends by looking back. Quiet stars do not promise discovery. They offer perspective. They show us that habitability is not loud, fast, or inevitable. It emerges slowly under restraint in systems that avoid disruption rather than overcome it. Life does not flourish where energy is abundant, but where change is limited. Not where the universe is dramatic, but where it is patient. This realization completes the arc. Alpha Centauri taught us where life cannot survive. The planetary filters showed us why most worlds never try. Quiet stars reveal where survival might actually endure. Together they form a single conclusion. The universe does not optimize for life. Life occupies the narrow spaces the universe leaves untouched. Stars that flare, less systems that evolve gently. Planets that remain stable for billions of years, these are not the rule. They are exceptions that persist because nothing forces them to change too quickly. And in those exceptions, complexity has time to accumulate. What we are searching for then is not company in the cosmic sense. It is continuity. The quiet stars do not call attention to themselves because they have nothing to announce. They simply remain, and that remaining may be the most important condition of all. In that sense, the search for life elsewhere becomes inseparable from understanding life here. Earth is not just a data point, it is a reference case. A planet that passed every filter not through strength or speed, but through sustained balance. The lesson of the quiet stars is not that life is lonely, it is that life is conditional. If others exist, they will not be obvious. They will be distant in space, distant in time, or both. Their silence does not imply absence. It reflects the same restraint that allowed them to survive. And if they do not exist nearby, that absence is not a failure of the universe. It is a consequence of its structure. The cosmos is not hostile. It is selective. The quiet stars remind us that awareness is not guaranteed even in a galaxy filled with planets. It must be preserved once it appears, protected from the same forces that erase it elsewhere. In the end, the most important habitable world we will ever study is the one that taught us how rare habitability can be, Earth.